Okay, today's topic is just one section, small section. So the question is, when you have many independent variables, how to estimate the slope, how to calculate your sample regression coefficient. So that's a question. So let me just remind you that in a simple regression, when you only have one x, we have a formula, right? The simple regression. The beta 1 hat was estimated by a ratio of sample covariance and a sample variance, right? The question is, can we have something like that when we have more than one x? That's the question, okay? So I try to provide some answer. Not a complete answer, but some answers to the question. So to make it simple, let's assume that we only have two x's, but you can increase it. So let's say that we have x1 and x2. But if you want to, you can go further. So let's erase this much and pretend that this is a multiple regression we have. So how to estimate these betas? We have the same principle. We want to minimize sums of squared error. Okay, we want to minimize this thing. When I minimize it, I have freedom to choose any value for beta null, beta 1, and beta 2. Okay, so I change these three values, try all different combinations until I achieve the minimum value of this function. So how to minimize a function? We already know the answer, right? So it's kind of repetition. So let me define a function g as a function of regression coefficient. And to minimize, I take the derivative, I differentiate them, and make them equal to 0. Right? We have three arguments, so I'm going to take three partial derivatives, just like before. So in my first equation, I take partial derivative of my function with respect to beta null, and I'm going to do that for beta 1, beta 2. Okay, this is the moment that you can utilize your experience with differentiation inside of the summation. So why don't you try? So take these three derivatives, okay, with respect to beta null, and write down your equation. You do it for beta 1, write down your equation, okay, and do it for beta 2 too. I'll give you a few moments. So that's the three derivatives, right? And once you have derivatives, we like to have the first order conditions, which is forcing them to be 0. It doesn't have to be 0, but it can be 0 at special points of those betas. And that special value, we call it as all these hats. Right? That's going to be the solutions of these first order conditions. So when you evaluate these equations specifically at these at these points, you can make them all equal to 0, hopefully. So that's our first order condition. Now, because that is 0, this 2 does not matter, right? 2 doesn't matter. 2 doesn't matter. Minus 1 doesn't matter. You just divide everything by minus 1. Same here, right? Okay, so let me simplify them. So in a sense, we have 3 unknowns, 3 beta hats, and 3 equations, right? So the goal is to solve them. So let's apply the summations to each of these components. So apply summation to yi, summation to beta null hat, summation to this guy too. So my first equation. So what is the summation of beta null hat? Do you remember? Beta null hat is a constant. N times. And beta 1 hat can be taken out, right? So that's my first equation. This gotta be 0. My second equation, I have summation of yi and x1i from here. So yi times x1i minus that is true. So I multiply x1 to everywhere. Equation 3. This time I multiply everything by x2. So that's got to be 0. Now, I noticed that the first term has no beta hats, right? But the other terms all have beta hats everywhere. So let's move these 3 terms to the other side, okay? Then we have something like this. Let's move these 3 terms to the other side. And let's move 3 terms to the other side. So again, we have 3 equations and we have 3 unknowns. So how to solve them? That's the question. Do you have an idea? A matrix can be very handy. So let me show you this trick. So I plan to rewrite this part using a matrix, okay? Let me explain. We have a 3 by 3 matrix and 3 by 1 vector. When I multiply them, this is the rule. Okay? I take a row in a matrix, and I take a column and multiply them one by one. So I have n times beta null hat plus summation x1i times beta 1 hat plus summation x2i times beta 2 hat, which is this side. And that is equal to summation of yi. Okay? So this is one way to rewrite the first equation. Again, you take a row, this time second row, take the column, multiply them. Summation of x1i times beta null hat, summation of x1i squared times beta 1 hat, which is this part, and summation of x1i times x2i times beta 2 hat. That's this. Is equal to summation of y and x1. That's this, okay? So far, matrix is just a convenient tool to rewrite 3 equations in a compact way, right? Now again, the question is, so this is the variable you're interested. We still have to solve these systems of equations. How to do that? So let's call it a matrix A, and let's collection of these beta hats as a big beta hat, and that seems to be equal to some number. Okay, so let's call it X. So that's a system. A matrix times a unknown vector is equal to another known vector, right? So that's something we like to solve. And the idea is take an inverse of this matrix and multiply on both sides. Okay? Actually, this is a quite simple idea. So suppose that you have 5 times some unknown b is equal to 2. How do you solve it? Now, everything is just a number. You take an inverse of 5 and multiply it in both sides, right? Inverse of 5 times b. Inverse by definition means that they cancel away and give you an identity, which is 1, okay, for scalar. And an identity times b is equal to b. That's a definition of an identity. Is equal to 2 over 5. So that's how we solved this one equation system. When we have 3 equation systems, we basically have the same idea. So the idea is to find the inverse of this matrix A and multiply them on both sides. Okay? So let me rewrite it. Now, A inverse times A inverse is just an identity. This time, it's an identity as a matrix, which is 1s in the diagonals and 0s otherwise. An identity times something is just that thing. So the solution we are looking for is a product of A inverse and X, which is this vector. So the job really reduces to a simple thing. Find an inverse of a matrix. Okay? We have 3 by 3 matrix. So how do you write down an inverse of a matrix? Do you remember? Probably in high school. Do you still remember how to get an inverse? G by G matrix. You didn't memorize it? So the thing is that it is hard. It's not easy when you have a 3 by 3 matrix. So I'm not going to take an inverse for this thing because I don't memorize. If you really have to, the method is you open Google and type inverse matrix of 3 by 3 something, okay? And pops up the formula. You can use it. But I have to convince you guys that this actually works. So let's simplify the problem. Let's consider a 2 by 2 problem, which is simply a simple regression, okay? And let's see whether this idea works. So the idea is we solve our system in this way, okay? When we have a 2 by 2 system, we have an intercept and a slope. So we are going to keep this part, these 3 parts, and we are going to drop the third element, okay? So that's 2 by 2. Let's write it down. Now, what am I doing? Now, we need to get an inverse of this matrix. Because there is only one single x, let me just call it x, not x1. That's the same thing. Okay? Again, your task is to find an inverse of this 2 by 2 matrix and multiply. Okay? It's easier, right? Can you do it? Do it now. I'll give you 2 minutes. So did you get this? Now let's focus on the second one, beta 1 hat, because that's the thing that we remember. Right? So let's see. We get the same formula that we remember. We already know. So beta 1 hat, the second element of this guy, is given as now what do you want to do? Do you remember that summation of yi is n times y bar? Same for xi. So this is going to be n squared times y bar times x bar. And same for this part, right? Now let's divide everything by n. Do you remember something? Do you remember the shortcuts? The sample covariance and sample variance? The shortcut basically says that the numerator is equal to and the denominator is equal to So this is the formula we remember. So basically, I just, so by reducing the problem to a smaller one, we just check that this is one way to get the solution that we want. So we're done. The last thing I want to say is that so sometimes a matrix can be very useful, right? So this is one motivation to learn some matrix things. And a second motivation these days is knowing a lot about matrix algebra is very important when you write down your code. So to write a good code, you need some knowledges. You need some experience in matrix algebra. So when you have some time, and time allows, take the linear algebra. Go to the math department. Take the class, okay? It's one of the most useful class for econ major. Okay, do you have any questions? No? I'll see you tomorrow.